Swayam Prabha. Digital India. Educated India.
Hello students, welcome to the class. So today we will be discussing about a special type of 4+2 cycloaddition reactions. So in the previous class, we have discussed elaborately the 4pi plus 2pi cycloaddition reactions in the name of Diels-Alder reactions. So during that, we have studied so many examples explaining the Diels-Alder reaction, and then we have seen the stereoselectivity or regioselectivity of the Diels-Alder reaction depending upon the different types of substituents present, and we have seen the applications of the Diels-Alder reaction, right. So now we will be seeing some 4+2 cycloaddition reactions with allyl cations or pentadienyl cations or oxyallyl cations, like, and we also see some more 4+2pi cycloaddition reactions that are named as 1,3 dipolar reactions, 1,3 dipolar reactions. Let us start today with 4+2 cycloaddition reactions with allyl cations. So 4+2 cycloaddition with allyl cations. So if you see a typical Diels-Alder reaction, there will be a diene like this and then a dienophile. So the dienophile may be an alkene or alkyne, right. So they add with each other, resulting in the formation of a cyclic adduct molecule under thermal conditions. So this should be represented as 4pi supra plus 2pi supra thermal reaction, right. So you will be seeing a cyclohexene molecule, whereas in the place of the dienophile, if you are using a cation, allyl cation, still this acts as a dienophile and adds up with the diene molecule and results in the formation of a 4pi supra plus 2pi supra reaction, it shows, and it results in the formation of this one. So what exactly we have seen here is the participation of a charged species as one of the reactant in the Diels-Alder reaction, right. So in the very beginning of our course, what we have discussed while discussing the properties of the pericyclic reactions means a pericyclic reaction will never produce any kind of charged species, right, by itself. But if the reactant molecules are themselves charged, they are charged species, the charge of that reactant molecule will be carried forward until the reaction, completion of the reaction. So there will be no change in the charge of the reactant molecule, though it is adding or it is undergoing electrocyclizations or it is undergoing some other pericyclic reactions. The charge will be seen in the case of product as well. So that means there will be no new creation of any charged species, but if the reactants are charged in nature, so then that will be carried forward, right, until the product. So that is what you can see here. So the reactant molecule is a charged species here, and without disturbing the charge, nature of the charge, the pericyclic reaction is happening and resulting in the formation of a product still holding the same charge, right. So what kind of cations can show this particular type of 4+2pi cycloaddition reactions means So, a pentadienyl cation can also show this type of reaction, cycloaddition, and allyl cation can also show as seen in the example, and oxyallyl cations can also involve in the reaction, right. So, we will see now the properties of the special type of pericyclic reaction. So, this absolutely follows the 4 pi supra plus 2 pi supra type of cycloaddition reaction, and this is also thermally allowed, similar to that of the Diels-Alder reaction, right. So, here as all the cycloaddition reactions or pericyclic reactions are not influenced by the polarity of the solvent. So, these type of molecules will also undergo the cycloadditions without having any influence of the polarity of the solvent, right. And then these molecules will undergo either stepwise reaction or concerted reaction, and that purely depends upon the nature of the reactant molecules as well as the reaction conditions. So, sometimes these reactions are named as 4 plus 3 cycloadditions. So, electronically they are absolutely similar to that of the Diels-Alder reaction. So, that is based on the number of electrons given by the diene part and as well as the dienophile part, they absolutely imitate the Diels-Alder reaction, similar to the Diels-Alder reaction. But based on the number of atoms involved, so they slightly differ with the Diels-Alder reaction. So, this number represent the number of atoms that are contributed by each of the individual partner. So, this 4 represents the 4 number of atoms, that is carbons in this case for the dienophile, and this 3 represents 3 number of atoms, that is carbons in the case of this dienophile, right. So, but electronically how this reaction should be given means, this is a 4 pi plus 2 pi cycloaddition reaction. If you see, this is using the 2 pi bonds, that is 4 electrons it is contributing, and this one because of the positive charge, so he is having only 2 electrons to be involved. So, it acts as the 2 electron contributing partner. Okay. So, let us see some more examples so that we will get better idea of this kind of allyl cycloaddition reactions. So, let us see some more examples based on the participation of the allyl cations or pentadienyl cations or oxyallyl cation. So, cyclopentadiene, if made to react with an allyl cation, it shows 4 pi supra plus 2 pi supra type of cycloaddition under thermal condition, and you will be getting this one, right. The positive charge will be still seen there in the product. If you have a molecule which can generate the allyl radical, for example, this molecule. This on treating with trifluoro silver salt of acetic acid. So, you will be generating an allyl carbocation. So, that allyl carbocation on reaction with any diene like this, under thermal condition, the product you are going to see is this one. So, alpha alpha dash dihaloketones, alpha alpha dash dihaloketones, upon 2 electron reduction in the presence of a metal like zinc or iron will produce the allyl carbocations, or which are called as oxyallyl cations, right. So, upon 2 electron reduction of an alpha alpha dash ketones, haloketones, in the presence of a metal like zinc or iron, so right, in their zero state, oxidation state, so will produce oxyallyl cations. So, which can involve in the Diels-Alder type reaction, that is 4 plus 2 cycloaddition reaction, to give the respective product. So, we will see such an example with this reacting with alpha alpha dash dibromo-ketone. So, in the presence of metals like zinc or iron in the zero oxidation state, initially this alpha alpha dash dihaloketone will be subjected to a 2 electron reduction process. So, with which in the reaction you will be seeing this one, okay, an oxyallyl carbocation. So, upon reaction with these two, what is happening here means right, metal. So, what is happening here? So, this is moving here and this pi electrons are coming here and this is moving there to form 2 new sigma bonds. So, as a result of which so you will be able to see this one where the 2 methyl groups are cis to each other, and this product will be approximately 48%. And along with this, you will also see this one, and this is approximately only 5%. So, another type of 4 plus 2 cycloaddition reactions are 1,3 dipolar cycloaddition reaction, or 1,3 dipolar reaction, cycloadditions, you can say, right. So, these 1,3 dipolar cycloaddition reactions are also similar to that of Diels-Alder reaction, similar to Diels-Alder reaction, and they also show 4 pi supra plus 2 pi supra cycloadditions. So, these are also nothing but 4 pi supra plus 2 pi supra cycloadditions. These reactions are also thermally allowed, similar to that of the Diels-Alder reaction. But where the change is coming means, in the case of diene, where in the typical Diels-Alder reaction, this should be the diene. So, there may be any kind of substituent, preferably an electron releasing substituent, which will activate the diene molecule in the typical Diels-Alder reaction. But what is seen in the case of 1,3 dipolar cycloaddition reaction means, instead of 4 carbon atoms or 4 atoms participating in the diene part, so you will be able to see only 3 atoms. You will be able to see only 3 atoms. Among those 3 atoms, again, at least one should be a heteroatom. At least one should be a heteroatom, like nitrogen or oxygen. Now you can see the difference, right, clearly, right. So this is a carbon skeleton with 2 pi bonds, and any kind of substituent is capable of involving in the Diels-Alder reaction. Either it is the normal Diels-Alder reaction or inverse electron demand Diels-Alder reaction. That depends upon the nature of the substituent, that we have clearly discussed in the previous class. Whereas in the 1,3 dipolar cycloadditions, so the 4 electron contributing partner, of course it is contributing 4 electrons similar to that of the diene in the Diels-Alder reaction, but it is having only 3 atoms involved. And out of these 3 atoms, one is for sure a heteroatom, and it might be either nitrogen or oxygen, or both may also be present sometimes. Okay. So typical Diels-Alder reaction helps you in the preparation or in the synthesis of a cyclic adduct, mainly based on the cyclohexene, right. Whereas this 1,3 dipolar cycloaddition reactions are special because they will give you a 5-membered heterocyclic ring system, cyclic adducts. 5-membered heterocyclic ring molecules will be synthesized. That is the excellent synthetic applicability of these 1,3 dipolar cycloaddition reactions. Okay. So coming to these 1,3 dipolar cycloaddition reactions, the 1,3 dipolar molecule which is contributing the 4 electrons is named as a dipole, and the dienophile which is must for the cycloaddition reaction may be simply either an alkene or an alkyne. So it may be either an alkene or an alkyne. Okay. So these are called as dipolarophiles. Dipolarophiles. So in the typical Diels-Alder reaction, we call it as dienophile. So here it is a dipolarophile. So whereas the 4 electron contributing partner is dipole, and these are dipolarophiles. These will contribute only 2 electrons similar. So these 1,3 dipoles are of 2 types. It may be allyl type, that is similar to that of an allyl ion. So specifically if you want to mention, it is like allyl anion type, which contains 3 atoms. Okay, I am not saying 3 carbon atoms, it contains 3 atoms. So out of these 3 atoms, 1 or 2 may be heteroatoms. Okay, and the other is propargyl allynyl type of 1,3 dipole. So coming to the structure, this allyl anion type of 1,3 dipoles are bent in structure. Okay, whereas this propargyl allynyl type of 1,3 dipoles have linear structure, and in both the cases the center atom must be nitrogen. So coming to the examples, so nitrones are the best examples of one of the best examples for allyl anion type of 1,3 dipoles. So what is nitrone? So it is this one. So, nitrogen is carrying a positive charge and oxygen is having the negative charge. The beauty here is always the center atom, the nitrogen, will hold the positive charge, whereas this negative charge can move from here to this one. That means the terminal atoms may have the flexibility of holding the negative charge, right. So, these are treated as 1,3 dipoles. So, that resonating structure also we can see C minus double bond O, this one. So, how this is happening? If this negative charge is coming here and this goes to the carbon atom. These are the nitrones. The next one is azomethane ylide, where again the nitrogen will be the center atom with the positive charge. Here carbon will be the with negative charge. Whenever a heteroatom, that too an electronegative atom, attached to some carbon structure and the carbon surprisingly is holding the negative charge, we call such kind of molecules as ylides, and this phenomena as Ampolang phenomena. So, this phenomena is called as Ampolang phenomena. I will write here, where the carbon, which is less electronegative than that of the heteroatom, is having the negative charge. Okay. This again shows the resonating structure and this way. And other one is azomethane imine. So, azomethane imine. So, instead of the carbon, if one nitrogen is present, so it is an imine now. And again it shows the resonating structure. Like this. Whenever this moves here, this goes here. So, here also this moves here, this goes here, right. So, these are some of the examples for allyl anion type of 1,3 dipoles. Next, coming to the propargyl allyl type of 1,3 dipoles. So, nitryl ylide is one of the example. So, these are linear in structure. Nitryl group is there, nitrogen, and ylide means the carbon is with negative charge and nitrogen is with positive charge. Okay. Now, here again there is a possibility of the resonating structure, C double bond N double bond C, minus charge comes here and plus charge. Yeah. So, this is the nitryl ylide, and the other is nitryl imine. So, if nitrogen is there, this is nitryl imine. Okay. So, the other example is diazoalkane. Diazoalkane. So, this is the diazoalkane. So, these are some of the examples for 1,3 dipoles which can involve in the cycloaddition reactions of similar type to that of the Diels-Alder reaction with 4 electron partner and a 2 electron partner. So, the 4 electron partner surprisingly now here is having only 3 atoms, and out of those 3 atoms 1 or 2 may be a heteroatom like nitrogen or oxygen. So, let us see some of the synthetic applications of these 1,3 dipole reactions, cycloaddition reactions. So, first we will see the synthetic applications of the nitrones. So, nitrones we have seen already. So, this is nitrone, right. So, these nitrones are generally used in the synthesis of isoxazolidines. Okay. So, isoxazolidines can be synthesized using the nitrones as the 4 electron partner in 1,3 cycloaddition dipolar cycloaddition reactions. What for these isoxazolidines are useful? So, they act as the starting materials for the synthesis of beta amino alcohols. Beta amino alcohols. And these nitrones, one good thing about these nitrones is they can produce 3 asymmetric centers in the product. 3 asymmetric centers in the product. So, highly stereochemically active molecules can be prepared. So, coming to the example, this is the nitrone, and if you react it with any dienophile like alkene or alkyne, you will be able to see a 5-membered heterocyclic ring system, right. So, if trans alkene is employed, so then what we will be getting here is the trans stereochemistry retained here, and also there is a methyl substituent here, right. So, this will also be an asymmetric carbon atom. So, 3 asymmetric centers are produced, one is here, so other is here and the other is here. So, 3 asymmetric carbon atoms. This isoxazolidines, this on reduction will produce beta amino alcohols, right, beta amino alcohols, and the stereochemistry is retained here. So, the stereochemistry is also retained here. So, this is the synthetic application of the nitrone molecules if participates in the 1,3 dipolar cycloaddition reaction. And coming to the regioselectivity of these molecules, if the dienophile is having any electron withdrawing group, so then the electron withdrawing substituent will come at the 5th position in the isoxazolidines, whereas if the electron withdrawing group is a nitro group, then you can see the nitro group on the 4th position. Okay. So, that is an exception. Apart from the nitro group, any other electron withdrawing group is taken in the dienophile. So, that will be seen at the 5th carbon atom. So, minus, and if the electron withdrawing substituent is attached to the dienophile, So, you will be seeing the substituent at the 5th position. If the electron withdrawing group is a nitro group, so then you will be seeing the nitro group on the 4th position. So, next is the synthetic application of the azomethane ylides. So, ylides are the molecules where the carbon atom adjacent to the electron negative atom is holding a negative charge, and we call this phenomena as Ampolang phenomena, right. So, these ylides, azomethane ylides, upon reaction with the dienophile like an alkene or an alkyne, will be producing pyrrolidins and delta 3 pyrrolines respectively. So, with alkene it produces pyrrolidin, and with alkyne it produces delta 3 pyrroline. Okay. So, upon further reaction, so these molecules, that is the pyrrolidin as well as the delta 3 pyrrolines, are converted to pyrroles. So, this is the azomethane halide where the negative charge is on the carbon atom, and this on reaction with an alkene undergoes 4 pi supra plus 2 pi supra cycloaddition reaction under thermal condition, and as a resultant it produces pyrrolidin. So, the methyl groups are cis. Whereas, with the alkyne molecule, it produces pyrroline. Okay. So, a heterocyclic 5-membered ring will be synthesized with the help of azomethane halides also. And finally, so we will see nitrile oxide, so which is a linear structure. So, this upon reaction with an olefin or an alkyne will produce isoxazoles. So, the next one is nitrile oxide. Right. So, how does the nitrile oxide look like? Nitrogen is with positive charge and this one is the negative, oxygen is with negative charge. This upon reaction with any alkene undergoes cycloaddition reaction and gives you the cyclic molecule right. So, or a double bond will be seen here and this is R dash. These are delta 2 isoxazolines. Whereas, instead of alkene, an alkyne is used. Right. So, what we will get is isoxazoles. Okay. So, such a beautiful 5-membered heterocyclic ring systems can be synthesized with the simple 1,3 dipolar cycloaddition reactions, which is almost similar to that of the Diels-Alder reaction and also shows you 4 pi sopra plus 2 pi sopra cycloadditions under thermal conditions. Okay. Thank you.